Welcome to The Explainer. Today, we are going to demystify one of the most powerful tools in all of statistics. It's a method for finding a real, meaningful signal in a world that is just full of noisy data. We're talking about ANOVA.
So let's kick things off with a classic puzzle, a problem that pretty much anyone who works with data is going to face sooner or later. Picture this. You've run your experiment, you've collected all your data, and you can see right there in the numbers that there are differences between your groups. But are those differences actually big enough to matter? Are they real? Or could it just be random luck? That, right there, is the fundamental question. And this isn't just for scientists growing crops in a field. This challenge is everywhere. Think about it. Do people who use social media a little, a medium amount, or a lot get different amounts of sleep? Is there a genuine price difference between Coke, Pepsi, and Sprite? It's all the same core problem. How do we compare the averages of 3 or 4 or even more groups? Now, you've probably heard of a t-test, right? It's a fantastic tool for comparing just two groups, say fertilizer 1 versus fertilizer 2. But the moment you add a third group or a fourth, the t-test just can't handle it. You need something more powerful. And that's where our hero of the day comes in. It's called Analysis of Variance, or ANOVA for short, and it is built specifically for this multi-group challenge. And that full name, Analysis of Variance, is actually the biggest clue you're going to get about how it works. At its heart, it's all about figuring out if the average results you see across a bunch of different groups are truly different from one another. So, like any good statistical method, ANOVA starts off skeptical. It begins with a default assumption that we call the null hypothesis. In our crop example, the null hypothesis would be all 3 fertilizers are basically the same. There's no real difference in crop yield, and any variations we're seeing are just random chance. The entire job of the ANOVA test is to see if we have enough evidence to prove that initial assumption wrong. Okay, let's get into the core logic, because once you grasp this next idea, the whole thing just clicks into place. It's actually really elegant. So here's the apparent contradiction. We want to know if the means, the averages, are different, but the test is called analysis of variance, which is all about how spread out the data is. So what gives? Well, the secret is that ANOVA is really clever. It doesn't look at the means head-on. Instead, it compares the variability or the spread of the data in 2 very distinct ways to figure out if those means are truly different. And this slide right here perfectly captures that core concept. It all boils down to comparing the variation between the different groups to the variation that's happening within each of those individual groups. The absolute best way to think about this is signal versus noise. The difference you see between the group averages, that's your potential signal. That's the effect of the fertilizer you're testing. And the variation inside each of those groups, well, that's just the background noise, the natural random spread you'd expect to see in any real-world measurement. So if the data points within each group are spread all over the place, and the group averages themselves are pretty close together, well, then the noise is just drowning out the signal. It makes it really hard to say if the fertilizer did anything or if you just got a few weirdly lucky plants.
But, on the other hand, what if each fertilizer group is a nice, tight little cluster of data points, and the averages of those clusters are really far apart from each other? Now the signal is coming through loud and clear over all that noise. You can be way more confident that your fertilizer has a real, measurable effect.
So how does ANOVA actually measure this signal-to-noise ratio? How does it tell us if the signal is strong enough to believe in? Well, it boils everything down to 2 key numbers. First, it calculates a number called the F value, and you can really just think of this as the signal-to-noise ratio score. It's literally the number you get when you divide the variance between the groups by the variance within the groups. So a bigger F value means a stronger signal. Simple as that. So when you run this test in your software, you're going to get a little table that looks something like this. You can see the F value right there for our fertilizer. But the number we really care about, the one that tells us the final answer, is right next to it. And that number is the p-value. The p-value answers a very specific, kind of backwards-sounding question. It asks, okay, let's pretend for a second that our fertilizers actually have no effect at all. What is the probability that we'd see a signal this strong just by pure random chance? So a teeny tiny p-value means it's incredibly unlikely that your result was just a fluke. In this case, our p-value is less than 0.001. That is way below the standard scientific cutoff of 0.05. So we can confidently reject that initial skeptical assumption and conclude, yes, the type of fertilizer does have a significant effect on crop yield. So we have a significant result. That's fantastic. But that actually leads us to our very next logical question. You see, the ANOVA test is kind of like a smoke alarm. It goes off and tells you, hey, there's a significant difference somewhere among your groups. But it doesn't tell you exactly where the fire is. It doesn't tell us if all 3 fertilizers are different from each other, or if maybe just number 3 is way better than the other 2. To pinpoint those specific differences, you have to run a follow-up analysis. It's called a post hoc test. A really common one is called a Tukey test, and what it does is go back and compare every single possible pair, 1 versus 2, 1 versus 3, and 2 versus 3, to tell you exactly which groups are statistically different from one another. Okay, let's just pull back for a second and appreciate what this tool really lets us accomplish. In a world that is just flooded with data, there is always going to be random variation. It's the background static of reality. ANOVA is this incredibly powerful technique that lets us cut right through that static and confidently identify a true, meaningful signal.
It's how we move from just observing differences to drawing real, valid, evidence-based conclusions. Thanks for joining us for this explainer.